copyright as well, so this talk specifically on water.
And our next speaker in this session is Leonardo Testi, and he will give the complementary discussion of dust evolution in protoplanetary.
Yes, I'll focus on the dust evolution, discussing the physical properties of dust evolution, theoretical models, and observations. Giving this talk here is gratifying to some extent because actually the most active groups working in these areas are here in Heidelberg at the moment. And also there are in the audience, obviously, a lot of people working in this field. I first have to apologize. I've discovered that your problems with the internet were due to my computer yesterday. So I decided not to use my computer now, and I have the presentation on the laptop. So I hope on the laptop of the conference. So I hope it will go through with no problems, okay? But let's see how it goes. If we have problems, you can surf the internet. Okay. Let's move on. I will only cover here a fraction of what we have in the chapter. And so I encourage every one of you to come and talk to any of us. The ones that are underlined here are the ones that are present at the conference, and talk to us about asking what we included in the review or not, okay, if it's not covered by the talk here. And another thing that I want to say just at the beginning is that emphasizing again that this is the place to be for studying dust growth. Next week at the Max Planck, up to on top of Königstuhl, Jürgen Steinanker is organizing a very nice focused workshop that will cover many of the aspects that I will discuss today, and I hope that I will not be proven wrong too much next week, but I'll be there and change the review in case it happens. Okay. So I don't need to go through the detail of the introduction because Dimitri had done a perfect job in doing this. I just want to say that obviously we are studying the phase I will be discussing the phase of evolution of dust that is connected to the priming sequence phase of the central star, when the disk essentially is isolated from the rest of the environment, and the material is evolving, hopefully, to form planet eventually. Okay, this is a plot from Jonathan Williams' review a couple of years ago, just to remind everybody that within all the uncertainties that we have in measuring the dust mass, we are lucky enough that a significant fraction of the disks have enough mass in the solids to produce a solar system type planetary system, and this is good given the fraction of exoplanets that are observed. It's good that we have disks that can produce them, contrary to the simulations of disk formation that cannot produce the disks that we observe. The other thing is that I want to say at the beginning is that this phase of evolution of the disk and formation of planets has to occur very fast, okay? This was also shown by Rob Jeffries, just to point out that this e-fold in time perhaps is a bit longer than what is mentioned here, and there is this very nice paper about this. But the point is that in a few million years, the average disk has to have evolved away from the optically thick dusty disk and into a planetary system, okay? So how we do this, and this is a plot inspired by one of the organizers, Kees Dullemond, and basically our problem is to go from here to submicron particles to here, to planets, and what we can do, and what I will discuss today, is this first phase, in some sense, of growth of particles, that is, in some sense, the initial conditions to the Dracones, the models that connect to the other observable that are on the other side of this diagram. Okay? And if you want to probe this growth from submicron to centimeter-sized particles, obviously you have to observe in the optical, in the infrared, in the first part, and then to go through really the large pebbles, you have to go into the millimeter and centimeter domain. So let's go a little bit on the physics of what we expect to happen. And these are laboratory experiments of, in this particular case, is a grain-grain collision. This is what we would like to happen. Two grains that get together, collide, stick, and get bigger, and stick, and form larger and larger aggregates. This is a collision as 0.9 centimeters per second speed, as you see here. Then obviously you have other collisions as a slightly higher velocity in a similar experiment, and unfortunately it's not happening exactly what you would have liked. The two grains don't stick together, they bounce away, so this is a little bit useless. If you increase a little bit more the velocity, then you might find yourself in even worse situation in which the collision is not productive, but is actually fragmenting you into smaller and smaller fragments. And this is at 2 meters per second collision. And as you can see from the debris at the end of the movie, they ran a lot of experiments on this. This is another possible outcome. If you have a small grains and a large target, you throw it to the large target, and then part of it sticks and part goes away. So these are the basic physical process that enter into this game of growing dust into larger and larger aggregates, and these are now being characterized relatively well in the laboratories in the last few years. There were a lot of experiments in this sense, and obviously more needs to be done, but is a good thing. And this is a summary, again, of the possible outcomes, whether you have similar grains or very different grains, you have good collisions, not so good, but still okay, and then destructive collisions. So the data that is taken out of the laboratories that characterize these processes are then used into disk models to basically model the grain growth and compare with observation. But before going there, obviously you have noticed that one of the main important parameters is the velocity of these collisions. If the collision is slow, they stick together. If it's very fast, it's likely that the situation is different, okay? So relative velocities are important. And what are the possible causes of velocity in the disk? Obviously, one thing is turbulence that steers around in the gas, that steers around also the small particles, and this is one way of having different velocities and getting together and collide. Another possibility is that if your grain sits in the surface of the disk, then obviously feels a gravity component toward the midplane, so it tries to go down. Obviously, there is a gas drag, and so grains of different sizes feel a different gas drag, so you have differential velocities among grains of different sizes that create collisions, again. Then we have this very famous process that was discussed at length before the start of the Protostars and Planets series, and is the fact that if you have a large grain, it wants to orbit at Keplerian velocity, and if you have a parcel of gas, this does not want to orbit at Keplerian velocity because it feels also the gas pressure, and so it's in a smooth pressure gradient disk. This is sub-Keplerian, and so there is a velocity difference between the two. The grain suffers a drag. The drag, again, depends on the size of the grain. So smaller grains are carried with the gas. Larger, as they grow, they feel more and more drag, and they start to move into the star. So you create a relative velocity between the grains, and this relative velocity, as you see from this graph, can go to large values, okay? As a function, this is the velocity as a function of the grain size. So you have these grains that have velocities much larger than the velocity that you saw before for the fragmentation. So it's clear that this is one of the major barriers in growing to large particles in disks, and this is known since the 70s as the meter-sized barriers as 1RU. So this is the summary of how the velocity of the collision, of the grain-grain collisions, these are sides of the two colliders, and these are the velocities that you expect from the different processes. And this is a summary of the results of the laboratory experiments. Depending on where you are on this diagram, you start growing from small particles So you start growing along a sticking with similar mass sides, and then at some point you hit the bouncing barrier that I showed at the beginning when your velocity is high enough to start bouncing. And if you manage to cross and you go in the wrong place of this diagram, then you are destroyed by the grain-grain collision. So the only way that you can grow is if you manage to surpass the bouncing barrier and go in the right way of the diagram in order to grow by essentially mass transfer, which was the last of the movies that I showed. This is a set of computations based on the processes that I showed before, and again, summarize the same problem. As you grow, you can grow in the green zones. At some point, you hit this bouncing barrier that you have to overcome somehow. And to overcome it in your computer, you just put 1 centimeter size grain, and the centimeter size grain is on the other side and can take over. And in a protoplanetary disk, we need to find the right computer where to put this large grain. So this is still a problem, although that's the idea of what we think is going to happen. Okay, so how this global disk evolution model works? You get your favorite disk model, you fill it with small dust particles, and you include gas, and add this dust-dust and dust-gas interactions, as I supposed. Then you go have a beer, since you are in Heidelberg, and then a little while you look at the results in your computer. And in the last few years, these are computational intensive things to do. That's why you need to get the beer in between. And several groups are running this type of computation. I will mostly show, for the benefit of keeping this short, the results of Til's computation, but in the review, obviously, we discuss all of them. Okay. After a while, when you came back in your office, you have this sort of plot. This is as a function of the radius on the disk. Okay, so this is 1 AU, 10 AU, 100 AU. This is the maximum, the grain size, and the color code is the grain size distribution, how many grains of each size you have. So you see basically that after a while you have grown large grains in the inner regions of the disk, in this case up to 10 centimeters, and in the outer disk you have millimeter or sub-millimeter size grains. Obviously, you can also go back of what was happening when you had the beer and look at how this was progressing. And you see that as things go, you grow grains first year, and then up to what is called the fragmentation, the drift or fragmentation barriers. And then after a while, you see that the grains start to move quite fast, actually, toward the star in these simulations. Okay, I don't want to go into the detail of this. This was just to show how a disk looked like, but Dimitri already did it very well. Again, this one is not very useful at the moment. I just want to tell you that for the talk, and only for the talk, I will focus on the sub-millimeter, so the mid-plane of the disk where most of the mass is and where we want really to grow into planetesimals. Okay? So how do we probe observationally these large grains and how we expect to be able to find them? As you grow the grains, the properties of the dust opacity coefficients obviously change, and that's the proxy that we are all using in the sub-millimeter. All this is obviously model dependent to a large extent, but what is a common feature of all the dust opacity models is that if you grow particles from sub-millimeter size grains into larger and larger aggregates, what always happens is that the sub-millimeter spectral slope of the dust opacity coefficient, okay, this beta value, if you approximate, well, it's not written here, if you approximate the dust opacity as a power law of the frequency with beta, this beta value essentially goes from being the steep value that you have in the external medium sub-micron size grains, beta 1.52. It flattens and it goes to a much lower value of beta equals 1 or even less, okay? Since the emission is optically thin, you can trace directly this by observing the disks in the submillimeter at different frequencies, so you have a handle on the maximum grain size of your population, okay? This is obviously not a new thing. This is one of the, Anila surely remembers these plots with Steve. These were observations exactly trying to constrain the spectral slope of disks versus protostars, trying to show that there is an evolution of grain sizes in the submillimeter. We now have more complete samples and samples based on more accurate interferometric observations. This is a compilation of data from a large number of surveys and from papers that used also previous references. These are different star-forming regions noted here, and these are the data values plotted in this diagram that is an observational diagram at this stage, which plots the flux at 1 millimeter scaled to a common distance, obviously, otherwise you cannot really compare, and the spectral slope in the millimeter. If you had a disk composed of sub-micron sized particles like the interstellar medium, all the points should be up here, okay? The fact that they are down implies most likely that you don't have interstellar medium dust. So if you now want to transform this diagram into something more close to what you want to physically probe, the flux is roughly proportional to disk mass. Obviously, there are caveats here, but it's roughly proportional to disk mass, dust mass. And the grains and the alpha is inversely proportional to the grain size, the maximum grain size in your grain size distribution. If you put those models of global disk evolution onto this diagram, turning off for a minute the radial drift, okay? So you exclude the physics of drift. Then you discover that you can reasonably fit this data with the models that have been developed for grain evolution in disks, which is nice. But you fit the upper end of the distribution. So one can think that you can move these by evolving the disk to lower masses or something like that. This is, again, now switching on radial drift, just to show you what happens. This is, again, the evolution of one of Tilt's model, again, in the radius, maximum grain size, and the distribution. And you see that you grow grains, and then you start to move them towards the star, and the grain size distribution goes down. If you plug in this model, this evolutionary model now in the same diagram that I showed before, they start in the right place of the diagram, but then they shoot up high because you remove selectively the large grains, and you remove a lot of mass relatively fast. And so you don't explain the population. To explain the population that you observe, you need to have a different process that stops this migration or slows down this migration. And this was explored by Paola, Keys, and Till. And basically, if you add pressure traps, this is again something that goes back into the 70s, because the first discussion of the effect of gas onto dust, into the particles, and pressure bumps was discussed in by Whipple in 1972. But if you put enough of these pressure bumps in this disk, then you slow down the drift, and you can, in fact, explain your population of data this way. You may question that the disks may not be exactly periodic oscillations. Obviously, yes, that was just a proof of concept. You can have different mechanisms that create these pressure bumps. And obviously, there are a lot of groups that are investigating these different mechanisms, and greatly likely they are making predictions for ALMA observations, which is great for us for the future, like Dimitri did for the gas. So we can use also the ones for the dust. And this is just one example for a different type of traps created by spiral arms that again confine the large grains, and this would be observable in the near future with the full ALMA, which is about to come. So basically, the scenario that we have is this one at the moment. So you have all these data points, you have the models, and you have this evolutionary track that goes this way if you can slow down the radial drift. Okay? So we assume that we can slow down the radial drift. What are the predictions of these scenarios? Basically that you have a fast grain growth, because you have seen from all the models the grain growth is extremely fast at the beginning. You have a grain size segregation, both vertically, I've not discussed this, but you have it vertically, and you have it also radially. And the gas to dust ratio also has to change because of the radial drift. Even if you slow it down, there is some drift. And so the dust, the large grains will concentrate mostly in the inner regions of the disk. The gas and the small grains carried over by the gas will spread out due to viscous evolution of the disk. And the other thing that we predict is that one should have dust traps to keep the disk alive to some extent. There is one thing that I will not discuss because I don't have time, and there is this fast grain growth and the fact that we expect that the grain growth may occur before the disk formation, in fact. And I have to apologize that I didn't have the stamina to go through all the abstracts of the posters. So I only pointed out here 3 posters from the previous session. There will be more posters in the next session. But I point out those from the previous session because they are not there anymore. And so you may want to go and talk with the people if you are interested in this process. They have been all looking at also other things as well, but also at the growth of dust in the earliest stage before the disk that I'm discussing here. Okay, another thing that you want to do to test the physics that you're putting in your models is to look at extreme environments, because always when you test the extremes of your things, you learn some things. And these are not certainly the most spectacular ALMA images that you have seen, I'm sure. Certainly they don't compare to what Steve has shown yesterday for the brick. They are simple little blobs, but ALMA for the first time is allowed to do detailed studies of disks around brown dwarfs at the level that we have been doing in the last few years in Titori stars with existing interferometers. And why this is relevant? This is relevant because if you go into this diagram, the brown dwarfs are in an extreme region of the diagram where it's not easy to grow dust. This can be done if you scale down the disk properties in the right way. And in fact, there is a few nice papers that show, for example, Farzana Mero showed that you can grow this dust in this disk if they have scaled down properties compared to the one in Titori stars. But it's also more difficult to keep them in the disk. The radial drift problem is more severe in these objects. And Paolo has been looking at this in quite some detail, and it finds out that you have to push the envelope of all your physical parameters in terms of the traps, in terms of the fragmentation velocities, in terms of the turbulence, in order to explain these 3 points with evolutionary models. Okay? So this is something that is going to be interesting, especially when the points here will not be 2 or 3, but will be a significant population. The other prediction that I mentioned, and want to spend a little bit more time, is the fact that we expect a gradient in the dust properties along the disk, with large grains in the inner regions and small grains in the outer regions. And these are 2 studies that were done a couple of years ago. One using essentially karma to basically trying to constrain again this beta as a function of radius across the disk. And this is obviously more complicated because you have to resolve it with high signal to noise at more frequencies. And this is one of the plots that are in the Stefan's paper from 2011, which basically show a more convincing, in this case, result of the evolution of dust of beta, actually, of beta from the inner regions to the outer region, where in the inner regions you have a beta that is very low, and in the outer regions you are consistent with a beta that is significantly larger. What blocks you in this study, I mean, the limiting factor is the fact that you need to have good signal to noise, good angular resolution, and broad wavelength range. So to overcome this problem, obviously, we thought that the EVLA can give a long leverage if you can sort out other emission problems that contaminate your dust emission. And so Claire Chandler put together a very big key program with the EVLA to use the full sensitivity and angular resolution to map at 1 centimeter essential and other frequencies, but the key thing is 1 centimeter, a number of disks, a statistically large sample of disks to determine the properties of the grain growth as a function of radius as a function of other system properties. And the first results of these big programs are coming out. This is a sample of the data that we are collecting on each object, in which you see basically that we are not only resolving very well the disks, but we have good signal to noise across the entire disk, also at the long wavelengths that are probed with ALMA. And this allows essentially to build these beta index profiles that are now beta from 1 centimeter up to 1 millimeter, roughly speaking, okay? So a large wavelength range. And this is convincingly showing that in the inner regions you have these large grains, and in the outer regions you have grains that are consistent with small particles, like in the interstellar medium, okay? Or consistent with the particles that can be carried by the gas, if you want, when it expands. And these are just a plot that I made just with it's just a guideline, because it's just using a sample dust model to derive from these beta values, which are the observed quantities, essentially, to derive the maximum grain size in the population as a function of radius. And obviously, the exact value, as I said before, depends on the assumption that you make on the dust properties. And the two lines are two regimes of Tilts models for drift-dominated and fragmentation-dominated limit. And again, also these limits depend exactly on the disk properties you assume. So you have to look at this as a guideline, but basically the guideline is that the observations are consistent with the predictions of these global models of evolution of dust in protoplanetary disk. Okay, the other thing that I want to touch, since we have been saying it, both Dimitri and myself, and also was also mentioned before, is the fact that it's now time to look in more detail at the coevolution of dust and gas, and take into account the fact that so far in all the models that I've shown, basically the gas-to-dust ratio is kept constant, and this cannot be, obviously. So we need to look at this difference. I'll show some observational results. These are results from last year, essentially, from CARM, I believe, where you have the dust disk, which is again millimeter-type dust because it's observed at millimeter wavelengths, and the big ellipse is instead the gas sides of the disk, just to show you the difference that you have. You can explain this difference if you assume that the dust properties are changing as a function of radius, obviously, okay? So you don't need to separate disks, obviously. And these are the results of some of the now many times mentioned HD 163-296 data, science verification ALMA data, where again you have the color plot is the CO disk, the first moment of the CO disk, showing the Keplerian rotation, and the contours is the continuum. And if you fit the two things separately, using a single dust population for the continuum, you see that this dust population that contains large grains is confined in the inner regions of the disk, while the gas extends to larger region. Obviously, this disk has also been observed in scattered light, and the scattered light emission goes away up to large radii. So you have small grains here that are filling the region that is not fit by the single population of dust. Okay, one last thing that is, I think, something that will be explored more and more in the coming year and will become possible with ALMA and with the next generation of infrared telescopes, infrared optical telescopes, is that we can now start to probe observationally the 3D distribution of dust in the disks, in the atmosphere of the disk, and on the midplane as a function of the vertical scale height and the radius. And this will provide essential constraints on the models. And this is the model that the authors fit onto this particular set of observation, which includes scattered light at different wavelengths and millimeter or submillimeter and millimeter observations, basically with different populations of dust grains in the different regions of these disks. This is an initial and very promising study for the future. The last thing that I want to discuss is the traps and how to slow down the radial drift. And I'll do this by showing this very nice ALMA cycle 0 data result from Nienke van der Marel, which came out essentially last month in Science. And basically, the key of the result is this one, which is the continuum image from ALMA at band 9, which shows essentially that the millimeter-sized particles are confined in one specific region of the outer disk of this transitional disk, okay? While if you look at the micron-sized dust in the infrared, you see that it populates the entire disk. So this means that if you want to see it in a cartoon way, this is how they show it in the paper, you have the small grains everywhere and the large grains confined in this area. And this is consistent with the large grains being trapped by essentially an asymmetry in the gas distribution caused by a planet inside the gap that creates a pressure bump that is both radial and azimuthal. And so you're basically confining the large grains very efficiently in this trap. Obviously, this trap does not solve the meter size problem because you have a planet already here, so it's a chicken and egg problem. But this is what we expect that might be able to also happen in pre-planets if you can create these traps that confine the grains and allow you to grow beyond the size. So this is my summary. I think that I hope that I'm convinced you that the grain growth physics has been constrained and is being constrained a lot in the laboratory by experiments now. We have a much better understanding on what the basic processes are. And also, I didn't discuss this, but there's also a lot of work in studying numerical simulations of grain-grain collisions, essentially, that go together with the laboratory experiments. These physics can be input into the models of disks that then, at this stage, they are reproducing quite well what we are observing in disks. I think the meter-size barrier is still with us since 1977. It's a little bit different than how it was envisaged at that time, but we still need to find a way to solve the trapping and slowing mechanism. There are several ideas. I think the point now is to observe them, and ALMA will allow to do that. The key development for the projects, for the developments for the future, in my view, are that studying more the early growth of solids before the disk, and because this can give constraints also that are in line with some recent, I didn't have time to go into that, but in line with recent constraints for cosmochemical studies of dating the large blobs into the meteorites of our own solar system. And the other thing is that both from a model and observational point of view, I think there will be enormous progress in the dust-gas coevolution, as also Dimitri has pointed out before me. And then the key thing that ALMA, I think, will be able to show is whether we really have small-scale structures in the disk that help solving the meter-size barrier. And I stop here.
Thanks, Leonardo. We have time for some questions. Let's begin here.
Hello. Hello. Yaroslav Pavlyuchenko, Russian Academy of Science. So in the models you mentioned, models of the dust evolution, is it taken into account that the dust grains actually can be charged, not neutral?
There are in the review we have a discussion of that. There have been studies of the effect of charged grains in grain-grain collisions. Yes, yeah, both theoretically and yeah.
Okay.
Kees?
Yeah, hello, Kirsten.
Arg, the expert.
No, no. I would like to ask, when we are of course now focusing a lot on the meter size barrier, but there are these two other barriers, the bouncing barrier you mentioned already by Andros Zom and Karsten Güttler, but also the charging barrier by Okozumi. And so my question would be, are there any ideas how to observationally test whether these barriers exist and, or what happens with these barriers?
That's a good point. I mean, it's not going to be easy to observe the sill-gold-grain interactions to see how they survive in the disks, this thing. But to some extent, in my view, what you have to, what I think that from the observational point of view we can try to see whether the large grains and the small grains are in specific regions of the disks. That's the trapping thing. And if you see that basically you are concentrated on special regions of the disk, then studying those regions might help telling you something. And obviously there are ideas on the model side on how you grow this barrier, you go over these barriers. There are the idea that the snow line, for example, can help in overcoming some of these problems by the evaporation and recondensation. And this again could be tested because now we have one could try to see whether the large grains are associated with the snow barriers, or the snow lines, for example. So at the moment, it's difficult to say what we will see, no, as usual. The prediction of the future is difficult. But I think the prospects of finding where the grains are growing in the disks and what are the characteristics of those regions are there.
Okay, I'm going to remind people in the balcony, we do have microphones at each edge, so I will be looking for you to ask a question. Let's go to Chris.
Yes, nice thoughts. I'm a bit worried by these findings of the low beta in molecular clouds or by ISO stages. I think it's very difficult to grow grains there to millimeter sizes. So my question is, have you investigated other mechanisms how you get low beta values, except in calculations?
Yeah, there is a big discussion about this, and maybe it goes detailed and we can take it offline. But
It's quite fundamental.
I think that the fact that in the inner regions of the envelopes of protostars, where the densities are relatively high, I believe that we are really tracing the growth of grains. Then you can discuss, I think it can be discussed how large are these grains and what are their properties, because relating beta to an exact grain size is not trivial, because it depends on the exact dimension. But they are not submicron sized particles, I don't think. In the clouds, there's been a long discussion in the literature, in the more diffuse clouds, of the relationship between temperature and the measurement of beta at higher frequencies, actually. So in the sub-millimeter regime, far-infrared regime. And there are opposite visions, and I'm happy to discuss them offline, because I think it's more specific. Yeah.
Okay, let's go over here.
Hi, Melissa McClure, University of Michigan. So I was wondering, in say a planet trap, you might expect, or sorry, a dust trap, you might expect to see both grain growth and an increase in the local dust to gas mass ratio. So there might be a degeneracy between the two. Are there observational ways that you could disentangle that from the submillimeter fluxes, or has anyone explored that?
No, yes, no. So yes, you do expect that. That you do expect always, I think. The point is that what I've been discussing, what you see in the submillimeter continuum is only the dust. You don't see the gas, obviously. the gas, the overdensity in the gas, and so the gas to dust ratio, you have to measure trying to sort out the gas chemistry and how the gas will emit in the different regions, which is not trivial, as we have been seen before. But the way to go is to try exactly to compare gas and dust maps. In the case of the dust trap that I showed, the gas is overdense by a small factor, but the millimeter-sized grains are all there. No? So the difference in the continuum and in the line emission is dramatic.
Paola?
Paola Caselli, University of Leeds. So I just wanted to follow up on the early growth. So I don't know how early that is, what do you mean by early, but in our work with Eric Quito for the, say, inner size of one of the prestellar cores that have been most studied, to reproduce the low temperatures that we have measured with the ammonia, with the VLA some years ago, we really needed to have larger opacities, and so that is like a factor of 4 times the thick ice mantles of Hoffenkoop and Henning. So that says that there is grain growth at the size scale probed by the VLA, which is about 1,000 AU. So I guess that if we can go even deeper, hopefully, with ALMA or something, we can actually probably even see that things get even bigger. So you may have actually the big grains, big probably micrometer size. I don't believe that can go much bigger than that, but who knows, in the early phases. One question I have, and that I hope is a quick question, is about the coagulation of these dust grains. I don't think I heard experiments done with icy grains, or maybe I just missed it, and I was wondering if that makes a significant difference in the time scale for coagulating dust in the disks if you have ice.
Okay, so the question I'll defer to Jürgen, who is the expert on what has been done in the laboratory. I'm not sure whether experiments with ices have been done. That I'm not sure. We're just starting. Yeah. Yeah, exactly. It's for the next chapter. Regarding the other thing, yes, I am perfectly aware that you have growth in the prestellar course, even from your studies, and in fact, you are in the review somewhere. And that's what I meant by early, yes.
We're now in the rapid fire round of short questions and short answers. Andreas?
Hi, my name is Andreas Jong from MIT. Hi.
Yeah, there.
Okay. Yes. So my question is similar to that. So condensation and evaporation can change the particle size distribution, especially close to the snow line. Yeah. Is it something that we will be able to see observationally, or are there plans to develop models to treat coagulation and condensation evaporation simultaneously?
Okay, there are models already developed, and I believe that, well, we have them in the references in the chapter, but Johan Andersen will possibly discuss this in his review. So, yes. As I said before, I think now we already observed the snow line more or less directly in this HD 163296 object, and the thing that one would do to test those kind of things is to try to measure the grain size across the condensation region, essentially on the mid-plane. And this can be done, but in the future.
And by short, I mean small in time. Second one here.
Yeah, Phil Lucas, University of Hertfordshire.
Yeah.
With reference to the EVLA data that you mentioned that Chandra is leading, you're trying to measure beta at 1 centimeter, but how do you distinguish between thermal emission from the dust and free emission from the gas? Because they can both be there.
Claire Chandler is leading the program, not Sean Andrews, but Sean is part of the project. We have multi-frequency observations at longer wavelengths. So basically, you dissolve the degeneracy by measuring the free emission at other wavelengths and correcting your observations at 1 centimeter.
Quick one in the middle, and then last to Morbi.
I'm Satoshi Okuzumi from Tokyo Institute of Technology. So my question is about the radial distribution of the beta. And you showed that the beta actually exceeds the interstellar value in the outer regions. But I think finally the beta value should converge to the interstellar values. So
Yeah,
my
well,
question
if
is,
you look,
is there observational data that shows that?
Yeah, if you look, don't take those, the error bars was also large, but if you look, and it was consistent, I believe, also with the ISM number, but if you look again at the opacities, at the values of beta as a function of you grow the size, actually there is, it goes, when you go from small grains to large grains, you have the interstellar medium value, then you have a bump, a resonance bump, and then it goes down.
That's
So
a theoretical expectation here.
Yeah.
So is there the supporting observation data?
Well, the uncertainty is too large to be sure.
Okay, final question, Morbi.
Yeah, Morbidelli from Nice. So you showed at the beginning the famous diagram showing the fractional stars with hot dust as a function of time decaying very quickly. Yeah. So what is now your current interpretation? Is that due to disk removal or planetesimal accretion?
I think, well, everyone has his own explanation, but there are reviews on exactly the disk dispersal, and I think I would refer to them rather than having a long discussion here in the interest of the coffee break.